This is our channel, a place where curiosity meets understanding and where every mystery of the universe finds its voice. In this journey, no question about the cosmos will remain unanswered. Why this universe exists, why it follows its rules and laws, why everything moves in such perfect rhythm, not by chance but by cosmic design. This isn't a place of confusion or speculation. Here, everything is explained through the lens of reason, rigorous, precise, and fascinating. Years ago, the Discovery Channel released a legendary documentary, a visual certificate of wonder that unfolded the story of space. That's where we begin, with a voice and a vision that aim to explain everything the universe hides. My name is Stephen Hawking, the voice says. I'm a physicist, a space scientist, a man whose body cannot move, yet whose mind travels farther than galaxies. Hawking's life became proof that even when the body is bound, the mind can be infinite. Through his computer, he spoke to the world, not from strength, but from pure intellect. He didn't need physical freedom. His thoughts were his universe. He sought to understand the deepest mysteries of existence, why the universe behaves as it does, why it follows its specific rules, and why these laws never break. Through every rotation of a planet, every pulse of a star, he believed there was one simple truth hidden beneath all the complexity, that everything in the universe might be explained by a single, unified theory. From the International Space Station, the glowing ribbons of the Aurora Australis shimmered across the dark sky, waves of light born from solar winds colliding with Earth's magnetic field. To Hawking, they were more than beauty. They were clues, symbols of a grand design waiting to be uncovered. He spent his life searching for those clues, and as he once said, "If we can find the theory that explains everything, we will know the mind of God." But reaching that understanding was no easy journey. It took humanity centuries, and it began in a small English town over 300 years ago. The year was 1665. England was reeling from the Great Plague, and a young man named Isaac Newton was forced to leave Cambridge for the countryside. What seemed like exile became the most productive solitude in scientific history. As Newton sat beneath an apple tree watching one fall to the ground, he began to wonder, why? Why does everything in the universe fall, move, and orbit the way it does? And from that question, the modern world was born. Newton discovered that there exists an invisible thread woven through the fabric of reality, a force that pulls everything toward everything else. He called it gravity. Gravity wasn't just a force acting on Earth, it was a universal law operating across the cosmos. Its strength depended on two simple things: the mass of the objects and the distance between them. Newton's equations changed the world. He showed that the heavens obey the same rules as the Earth, that the fall of an apple and the orbit of the moon were guided by the same invisible hand. And because of his discoveries, humanity began to measure, predict, and control the very fabric of reality. Even today, centuries later, we're still walking the path Newton paved, searching, testing, and questioning. We look at rainfall and radiation, stars and atoms, all through the mathematical eyes of Newton's law. We build on his shoulders, just as he once built on the ideas of those before him. One of those great minds who followed was James Clerk Maxwell, a man whose genius would shape the modern world. In 1861, Maxwell began his groundbreaking experiments that forever changed our understanding of electricity and magnetism. He discovered that when a magnet is moved near a wire, it creates an electric current. And when an electric current flows through a wire, it behaves like a magnet, bending the needle of a compass. Through these insights, Maxwell realized something extraordinary: that electricity and magnetism are not separate forces at all. They are two faces of the same coin. He unified them into a single concept, the electromagnetic wave. Maxwell's equations revealed that these waves travel at an astonishing speed, 299,338 kilometers per second, the same as the speed of light itself. That discovery was a spark that lit the modern world. He understood that light itself is an electromagnetic wave, intertwining electricity and magnetism in perfect harmony. This revelation became one of the greatest moments in the history of science. From it arose the foundation of every electrical and communication technology we rely on today, from computers and washing machines to satellites and Wi-Fi. The universe had revealed another piece of its grand design. The power of electromagnetism illuminated our Earth, shaping our technology, our cities, and our very understanding of light itself. But beyond the expected discoveries, something even more profound was waiting to be found. James Clerk Maxwell's equations had revealed a massive clue, one that hinted at two fundamental forces working together in perfect balance. And by the end of the 19th century, scientists believed they were on the verge of unlocking every mystery of the universe. Yet, as often happens in science, a single unexpected experiment would change everything. An American scientist named Albert A. Michelson, along with his collaborator Edward Morley, set out to measure something almost impossible: the motion of the Earth through what they believed to be a mysterious substance filling all of space, the ether. At that time, physicists thought that light, like sound or water waves, needed something to travel through. They imagined that the entire universe was filled with this invisible medium, a silent ocean through which light waves rippled. The idea was simple but elegant. If light travels through this cosmic ocean, then its speed should change depending on the Earth's movement, just like how a boat moves faster when sailing with the current and slower when going against it. Michelson and Morley reasoned that as the Earth moved around the Sun, it must be passing through this ether wind. If they could detect a difference in the speed of light in different directions, say when light moved with or against this cosmic wind, it would confirm the existence of the ether once and for all. So they built one of the most precise instruments of their time, the Michelson interferometer. With extraordinary care, they split beams of light and measured how long they took to travel in different directions. If the ether existed, one beam should reach its destination slightly faster than the other, but when they looked at their results, there was no difference. No matter which direction they measured, toward, against, or across the supposed ether wind, the speed of light was always the same. This discovery stunned the scientific world. It wasn't just unexpected, it was impossible according to the theories of the time. The experiment had failed to detect the ether, but in doing so, it had revealed something far greater. Light didn't need a medium. It traveled through the vacuum of space, completely independent, its speed unwavering and absolute. This single observation shattered centuries of assumptions. Even though Michelson and Morley were disappointed, history would prove that their failed experiment was one of the most important in science. Their results became the foundation for a revolution in physics, one that would change our understanding of space, time, and reality itself. At the dawn of the 20th century, a young man named Albert Einstein appeared, a mind destined to redefine everything we knew about light. Einstein was fascinated by a question that had haunted him since childhood. What would it be like to ride alongside a beam of light? He imagined himself chasing a ray of light through space, wondering what he would see if he could keep up with it. Would it appear frozen? Would its waves stand still? This thought experiment would later become the spark that ignited his theory of special relativity. To understand his thinking, imagine a child playing with a toy train. A train that, in Einstein's imagination, could move faster and faster until it nearly reached the speed of light. He realized something profound. Motion is relative. If you're sitting inside a train moving at high speed and you throw a ball forward, its speed adds to that of the train. But light doesn't behave that way. Even if you're moving toward or away from it, the speed of light never changes. It is constant, the same for everyone, everywhere at all times. To make this clearer, Einstein imagined another thought experiment. Picture a train racing down the tracks. Inside, a person in the middle of the compartment lights a cigarette lighter. Two beams of light shoot out from it, one toward the front of the train, one toward the back. Now, imagine two observers standing at equal distances from the center, one near the front and one near the rear. To the person inside the train, both beams of light reach the ends of the compartment at the same time. But to someone standing outside the train, watching from the platform, it's different. Because the train is moving forward, the light heading toward the front has to travel farther. It's chasing the motion of the train. The light heading toward the back, however, meets the rear more quickly because that end is moving toward it. So, from the outside observer's perspective, the two flashes don't happen at the same moment. The conclusion was shocking. Time itself was not absolute. Events that appear simultaneous for one person might occur at different times for another. Einstein had uncovered a truth that defied centuries of belief. The speed of light is constant, but time and space themselves are flexible. This was not just a theory, it was a new vision of reality. It meant that space and time were woven together into a single fluid fabric, one that could stretch, bend, and twist depending on how fast you move or how strong gravity pulls. From the failure of the ether to the brilliance of relativity, humanity had taken another step toward understanding the grand design of the universe. And once again, everything we thought we knew about reality, from motion to time, had to be rewritten. Now let's pause for a moment. What does this all really mean? It means that we can never say for certain whether two events happen at the same time or not. The truth depends entirely on where you are, on your point of view in space and time. If we take that same idea and scale it up to the level of the universe, things become far more tangled and complex. Reality itself depends on where we stand within it. How can we truly know what's happening if we're inside the very universe we're trying to observe? Einstein's theory of special relativity gave us the answer, a radical idea that changed physics forever. He revealed that truth itself is flexible, because time is not absolute. It can bend, stretch, and flow differently depending on the observer. The very fabric of the universe is not rigid, it's elastic. This flexibility of time was something completely new to physics. Einstein showed that time and space are not separate entities. They are interconnected, woven together like threads in a cosmic tapestry. Just as electricity and magnetism are linked through electromagnetic fields, space and time are fused into one continuous fabric, space-time. And just like waves in a pond, this fabric can ripple, twist, or bend. Einstein discovered that gravity is not a mysterious force pulling objects toward each other, as Newton had thought. Instead, gravity is the warping of space-time itself. Massive objects like stars and planets bend the fabric around them, curving the paths of everything nearby, even light. To understand this, imagine a small wooden boat floating across a calm lake. When the surface is perfectly smooth, the boat moves straight and undisturbed. But now imagine a deep whirlpool forming in the lake, a vast pit opening beneath the water. The boat is drawn toward it, its path bending as the lake's surface deforms. That's exactly how space-time behaves around massive celestial bodies. The smooth flow of time and space becomes distorted by gravity. The greater the mass, the deeper the curve. Planets, stars, and black holes all create these invisible wells in the fabric of reality, pulling everything around them into orbits like boats caught in a cosmic whirlpool. On Earth, this curvature of space-time is what we experience as gravity. Einstein saw this invisible geometry of the universe, the hidden machinery behind everything, and realized that space and time were not just passive backgrounds. They were active participants in the cosmic dance. 10 years after proving the constancy of the speed of light, he revealed that gravity itself was the distortion of space and time. This revelation brought humanity one step closer to unlocking the secret key of the universe. But even Einstein, with his incredible insight, knew that his work was incomplete. He had seen how the universe functioned, but he didn't yet know why it worked that way. His theories explained gravity and motion on a large cosmic scale. Stars, planets, galaxies, but they couldn't fully describe the strange, invisible world inside the atom. Physics had entered a new era. The focus shifted from the infinite to the infinitesimal. In 1909, scientists in Germany and across Europe began exploring the realm of the very small, a mysterious, turbulent world where the rules of everyday physics seemed to fall apart. At this microscopic level, everything behaved unpredictably. Particles could be in two places at once. They could disappear, reappear, or pass through barriers that should have stopped them. This was the birth of quantum physics, the study of the smallest building blocks of the universe. To make sense of this, physicists often used analogies. Imagine a soccer player striking a ball toward the goal, with defenders standing in front trying to block it. In the everyday world, we know how this works. The ball takes a clear, predictable path. It either passes through or gets blocked. But in the quantum world, it's completely different. Here, the ball, a particle like an electron, doesn't take just one path. It takes every possible path simultaneously. It behaves like a wave of probabilities spreading through space and time until it's observed, and only then does it choose where to be. It's a strange and unsettling truth, but the deeper scientists looked, the stranger it became. Newton had explained the motion of planets. Maxwell had unified electricity and magnetism. Einstein had bent time itself. Now physicists were facing something entirely new, a universe that defied logic, where certainty no longer existed. Einstein once said, "God does not play dice with the universe." But in the quantum world, it seemed that dice were being rolled everywhere all the time. By the mid-20th century, brilliant minds like Richard Feynman emerged, men who could visualize this chaos and bring it to order. Feynman proposed that instead of trying to predict a single outcome, we should calculate the probabilities of all possible outcomes. Every particle, every photon, every quantum event, all governed by probability, not certainty. This idea didn't just reshape physics, it reshaped our understanding of reality itself. What started with Newton's apple had grown into Maxwell's fields, evolved into Einstein's relativity, and now descended into the surreal world of quantum mechanics, a realm so strange that even our best minds could barely comprehend it. It was as if the universe was playing a hidden game, one that we could glimpse but never fully master. A game where time bends, light remains constant, and existence itself is uncertain until the moment we look. This is Richard Feynman, gambling with the parties of science, but his mind quantumed the mathematics of his own choice. He couldn't claim to have electronics and players if he hoped to put the ball number once on his right target. Based on possibilities, he made rules on which perhaps a special quantum event was founded. When they explored the world, knowledge also emerged out of the bridge of examination. Subscribers had helped greatly, giving a huge opportunity to resume the search for the grand design. On a small scale, physicists now began to look for ways their principles could be applied to the smallest things, to the world of atoms, where the center and surroundings are made up of other forces that say, subscribe, and where time itself vibrates. Yes, let's think of it like a violin, the way its strings vibrate. Just like that, the universe vibrates in different varieties, the way the strings of a violin produce different tones. That is the essence of what it describes. Based on the principles surrounding our universe, it's said that the vibration of stars generates massive microscale distortions in space-time, and it does this in 10 dimensions, where minds rotate in patterns that form the basic causes of creation. But when those vibrations occur in another way, they form a different kind of tension. Now, from the string theory of physics, we can find out why this happens, how these vibrations create the music of the universe, the tones that explain why physics exists in all pitches of reality, how stars are born, or how they die. Just like the corn that grows and dies, stars too are born and fade away. Look at something simple, like a paper roll falling to the ground or a magnetic compass finding north. These might seem minor, but their basic workings are profound. Even today, there are countless variations, countless children of this day formed together on a vast MP3, and no one yet fully knows what it means or what it truly is. It's something of a mystery. That much we have yet to uncover. But before completion, this MP3, this universal melody, continues to play. From Maxwell's discoveries to this day, it has been a long journey. A journey that brings us to a new era, one that could be a historic turning point. I was thinking about this with my colleagues at the Perimeter Institute near Toronto. We were imagining something extraordinary, that the universe itself might not be the only one. The most shocking realization wasn't the existence of our universe, but that there could be millions, even billions, of other universes beyond ours. To understand it better, remember again that the strings, like the ones of a violin, produce harmonies. Out of the tiers of music arise the vibrations that give birth to stars. From these vibrations, immense power emerges, shaping everything that exists in our universe. But we must not forget, this cosmic music resonates far beyond the borders of our reality. If you look closely, you'll see the different cosmos, each vibrating at its own frequency. Some universes may never form stars or planets. They remain dark, silent voids. But others, like ours, can create life, light, and constellations. And one day, perhaps, those universes that mirror ours will reveal themselves. Reflections of the same pattern, the same design. That means our universe exists exactly as it must. Balanced, harmonious, alive. Obviously, our universe is right to exist. The results we have discovered, which once seemed unimaginable, now point toward the ultimate key, the secret code of the cosmos. It's comforting to know that the same system of laws, the same mathematical rhythm that governs everything, is what we call the grand design.